Everybody. We are going to take a look at chemical equilibrium, one of the most important concepts in chemistry. Hopefully you've already taken a look at the online tutorial, so you have a pretty good idea of what's going on. We're going to take a look at it from a more mathematical perspective. And this is going to be great because now we're going to know why some reactions have a single arrow and some reactions have a double arrow. Sometimes we say that they go to completion, and sometimes we say there's no reaction at all. So let's take a look at this generic reaction. You don't have this slide. And we can see that as A goes to B, the rate goes down as the reactants use up. As B, the reverse reaction, goes to A, the rate increases as we get more and more B to have around. So let's see what happens. And eventually we hit a point where the forward rate and the backward rate are the same. Not the concentrations, the rate. Let's take a look at what that means for an actual chemical reaction. So here we have N2O5 breaking down to NO2 and O2. The reverse reaction also happens. So let's see what happens. We start with 0.02 molar N2O5. We don't have any NO2 or O2. And let's see what happens when we start the reaction. We start making NO2, that's the orange. We start making O2. You can see we start making NO2 much more quickly, 4 times as fast. And we start using up the N2O5. And that's continuing to happen, and you can see right around here the shape of the curve is starting to change. We're going to talk about reaction rates later, and we'll take a look at why those start to change. And we're going to hit our next important point when we hit TE. That is the time at which they reach equilibrium. So let's take a look at these concentrations, and let's see what happens to these concentrations as we continue for the rest of the time. Nothing. What that tells us is that at a macroscopic level, looking at the container, we do not see any changes. What you hopefully saw in the tutorial, and what you definitely saw before in the last slide, is that the reaction continues to happen in both directions, but we don't see any macroscopic changes. And you can see here that we need to have a closed system. So here I have some water in liquid form in a closed box. Closed yet expandable. No water is in the gas phase. And we're going to see what happens as we look at this reaction over time. The vaporization and condensation is both happening, but right now it's vaporizing much more quickly. So you can see things moving into the gas phase. You can see the rates are starting to catch up. And now equilibrium is reached. The rate at which the liquid water leaves is the same rate as the gaseous water molecules go back to the liquid. That's what's happened in any closed container. However, if it's an open system, we're not going to reach equilibrium. That's why if you have a closed bottle of water, you'll always have some water vapor above the water. We talked about that way back when we talked about gases and vapor pressure and the vapor pressure of water, and we could look that up on a chart. But in an open system, so if I just have a glass of water, it will just continue to evaporate and evaporate and evaporate. We'll never reach equilibrium. All right, let's talk about what we're going to call the equilibrium constant capital K. Make sure it's a capital K and not a lowercase k, because a lowercase k is going to be different later on. K subscript EQ for equilibrium constant is an experimentally determined number that is the ratio of products over reactants. So going back a page or two, we could calculate an equilibrium constant if we knew, which we do, the concentrations of products over reactants. We're actually going to do that later. But before we can calculate an equilibrium constant, we have to find an equilibrium expression. An equilibrium expression, let's use a larger eraser. There we go. Is the products to the power of their coefficients over the reactants to the power of their coefficients. This is called the law of mass action. And we'll see a couple of different kinds. We're going to see Ks with a lot of different subscripts. Kc is molar concentration, where you see something in brackets, that's the molar concentration. Kp is the partial pressures, where P sub x is the partial pressure of x. For now, and the rest of this lesson, we're going to stick with molar concentrations. So let's take a look at how we can write an equilibrium expression. There are several rules. In a Kp, it's only the partial pressure of gases. If they're solids or liquids, we ignore them. In a Kc, it's only the molar concentration of solutions or gases. If it's a pure liquid, a solid, we ignore them. And we have the pressures or concentrations raised to the power of the coefficients in the balanced chemical equation. And for those of you who like to forget units on things, you'll be happy that we don't use units on these. So let's take a look at them. Here I have P4, it's a solid, plus chlorine gas makes 4 PCl3. It is the ratio of products to the power of the coefficient over reactants, except that would be wrong. Because we don't include solids. So it is PCl3 to the 4th power over Cl2 to the 6th power. We completely ignore the phosphorus solid because we're looking at the relationship in the changes in concentrations. Phosphorus, being a pure solid, has no concentration because concentrations are moles per liter. Those are variable in a mixture. So we're only looking at things where their concentrations can change. So let's take a look at a couple of these. I have 2 molecules of water, of hydrogen, and a molecule of oxygen, making 2 molecules of water vapor. Products over reactants to their powers. The equilibrium expression is K equals water squared over hydrogen squared oxygen. Now let's take a look at one that's very similar. The reactants are the same, but now it's water vapor, or sorry, liquid. I can't use liquid water. It doesn't have a concentration exactly. So we'll just use a 1. K is 1 over the hydrogen concentration squared over the oxygen concentration. Let's take a look at a third one. Ammonium nitrate breaks down into nitrogen and 2 molecules of water. Ammonium nitrate's a solid, so it's not going to be part of the equilibrium expression. I don't know where the K went there, but let me add it. And here's our last one. Tin 4 oxide and carbon monoxide make tin and carbon dioxide. Note that the tin and the tin 4 oxide are solids, so they're not part of the equilibrium expression. Starting to see how this works? Take a look at the next set. Pause the video and try to write these. All right, do you think you have them? Let's take a look at them. This top one is going to be really important. We're going to use this reaction a lot later on. Ammonia squared over hydrogen cubed nitrogen. 2 NO2s over N2O4. PCl5 over PCl3 and Cl2. CO and H2O over CO2 and H2. This is a really important reaction. We'll talk about what that is later. Hydrogen peroxide, aqueous, so it's a solution, breaking down into liquid water and oxygen gas. The liquid water isn't part of the equilibrium expression, so we have O2 over hydrogen peroxide squared. And ammonium chloride breaking down into ammonia and hydrogen chloride. Remember, ammonium chloride is a solid, so it's ammonia over times HCl over 1, technically. But anything over 1 is itself, so we don't have to worry about that. So now we can write equilibrium expressions. In the next little video, we'll figure out how to do calculations with them.